Time's 9 o'clock. Let's get started here. So project number 3 is due on Tuesday at noon. Test number 3 is coming up Wednesday, December 4th. That's really coming up fast. At the end of class, as I mentioned on the listserv post, we will be doing instructor evaluations. Are there any questions before we get going here today? Okay. So we were talking about nearest neighbor classification methods last time. Just to really briefly review, these nearest neighbor methods work quite simply. Let's say we want to classify a particular observation into one of 3 populations. What you do is you simply look at that observation relative to its nearest neighbors, or in other words, observations that are close to it. If, let's say, we had k equal 3 nearest neighbors, and let's say 2 of the observations came from population 1, 0 from population 2, 1 from population 3, well, then you would classify your observation of interest into population number 1 because it had the most nearest neighbors, or most observations in those nearest neighbors. The only thing that can get kind of a little bit complicated is about how do you handle ties. And we spent a lot of time talking about how to handle ties last time. Also, we were talking about last time, well, how do you end up actually choosing k? Do I want k equal 1 nearest neighbors, or nearest neighbor, or do I want k equal 3? Do I want k equal 10 nearest neighbors? And there's not necessarily a really good way to do it other than just try a bunch of different values of k and see what happens. And you choose then the corresponding value of k that gives you then the highest correct classification rate.
Is there any, is there a k that's too large? Even if it's
Other than, let's say if you use k equal n. Well, you're just using then the whole data set, and simply then the proportion of observations that are from one population is then the probability. Typically you will not see people go too large with k. The smaller k is essentially the simpler the method is. So how do we choose k? And we just left off on page 11 last time, where we were going to take a look at how we can choose k with respect to the place kicking data set. And what we're simply going to do for k equal 1 to 10, excuse me, basically apply these nearest neighbor methods to both the validation data set and also via cross-validation to the original data set. And we're going to look at the correct classification rates. So to do this, the easiest way is to use a for loop. We've talked about for loops in this class before, and this is what it looks like. Let me actually come over here to 10. So the first thing I'm going to do is set a seed. Remember, you should always set a seed before you apply k nearest neighbor method, because depending upon how ties are handled, or because of how ties are handled, some randomly selected populations might be chosen. So to be able to reproduce your results, you should always choose a seed. Then, I'm going to create an object called save.results. It's going to have 10 rows, 4 columns to it. The 10 rows correspond to my 10 different values of k that I'm interested in. The 4 columns are going to correspond to, and I have it written here, or typed here, column 1 is going to be the corresponding value of k. So I'm going to put the value of k in column 1. Column 2, I'm going to put the correct classification rate for the failed place kicks. Column 3 is going to be the correct classification rate for the successful place kicks, and column 4 is going to be the overall correct classification rate. I'm also going to create an object called save.results.cv, which contains then the results from cross-validation. And notice I'm initializing these matrices with NAs just as kind of a placeholder until I actually put the results in there. So I begin the for loop by saying for k in 1 to 10. So the first time through the loop, k is going to be equal to 1. Then I simply basically use the same kind of code that we had solved previously when we applied these k nearest neighbor methods. Where first of all, I'm going to use the knn function. My training data set, I'm using the standardized values from the original data set. We had found z last time. My test argument is going to be my validation data set. Again, standardized values. Excuse me. Then I apply then, just a second, I need to write into it to myself. Then CL stands for classifications. This corresponds to, from the original data itself, the population numbers. 0 for failure, 1 for success. My value k that I'm actually using. And then I didn't really need this, and I guess if I were to write this code again, I would just simply delete it like that. Prob equal true, remember those gives us the probabilities. Well, we're not going to, in terms of probability, that it should be from population 1 or excuse me, probability should be classified into the failure population or the probability classified into the success population. We don't need that here. We're not actually looking at those probabilities. Oh, my mouse isn't working. Turn it off and turn it back on. See if that helps. Yep. Okay, so I'm going to put the results into NNC. And remember what those results are at NNC is just simply the classifications. That's the main thing you're getting out. I'm also going to create an object called nnc.cv, and I'm going to apply the knn.cv function to it. So this allows me to do the cross-validation. Again, you don't really need then the prob equal true part. Then I'm going to use my summarize.class function to come up with the correct classification rates. So we've looked at this before, so I'm going to put then the validation results into nnc.accuracy and the cross-validation results into nnc.cv.accuracy. And then lastly in this loop, I'm going to put the results from summarize.class into my save.results matrix. That's going to save, k and also the correct classification rates. So as you can see here, I'm going to put into row k of my matrix. I'm going to combine together 4 things. The value of k, I'm going to pull out the correct classification rates for the failures, pull out the correct classification rates for the successes corresponding to the correct component, and then also the overall accuracy, pull that out as well. Do the same thing for the cross-validation results. And here we go. This is what we get. It runs really fast. And so we can see, for example, when k is equal to 1, the correct classification rate for the failures with the validation data set was 68%. For the successes, the correct classification rate was 96%. Overall, about 93%. Jump back over here to Word. Are there any questions about how this for loop works? Okay. Now, I think the easiest way now to look at all these results that we got here, and then to help us then choose a value of k, I think the easiest way to approach this is to do a plot. We'll take a look at the actual code for the plot shortly, but let's take a look at the actual plots first. Let me see if I can zoom in nicely here. And so those are then the plots. Just a second here. So you can see, for example, with the validation data set, the overall accuracy is actually decreased a little. as a function of K. For the successes, the rate's actually going up a little bit, and for the failures, the rate's going down as a function of K. Also on this plot, I plotted, well, what was the best discriminant analysis method? What did we get for that for the overall correct classification rate? And that's plotted as in the dashed line that goes across the plot. And so we can see that nearest neighbor methods tend to do a little bit better than the best discriminant analysis method, at least with the validation data set. Now, also, hopefully you remember, too, that, I was a little bit concerned about, were some of these, for the lower values of K, were those really accurate or not? And, we discussed reasons why I without going into all the details again, why I was a little bit concerned. And I still am. Let's take a look at also the cross-validation. So we can see that as K is increasing, we can see that my overall rate is increasing a little bit until it gets to kind of a plateau. And for the successes, the rate is increasing. For the failures, the rate is decreasing as a function of K. Okay. So how can we then use this plot to pick a particular value of K? Well, obviously, how about we just, to make this easier, how about we just focus on the overall rate for now? If you're to only use the overall rate, what you're looking for, of course, is then where is the highest value for the correct classification rate as a function of K. And we can see that for cross-validation, it seems to tend to happen right around there. So you have multiple values of K to choose from. For the validation, you can see that it happens for the lower values of K, which is kind of in contrast to what we saw with the cross-validation. But again, still, I am a little bit leery about using those. But we do see kind of maybe a leveling off here, and then, and if you notice, it's really not too much different towards the larger values of K compared to the middle values of K. You could just be seeing some variability. So, just because you see one value at 0.96 and another value at 0.95, that does not necessarily mean that the 0.95 is really worse than the 0.96. There's, you should expect some variability. So overall, what I see here is that, if I had to pick, I would choose maybe K equal 4 to maybe about K equal 7 about. You can see that there can be room for multiple, or one person might have one interpretation for what the value of K should be. Another person might come up with another value, especially in a plot like this. But generally speaking, I would take somewhere between 4 and 7. Of course, the lower value of the K, you could say the simpler your statistical method is too. So that's why, I'm not necessarily going up to K equal 10. I really don't see any benefit. And I think this also gets then to the question that we had earlier. Well, is there any limit to essentially what K is? Well, typically what you will see in these kinds of plots is that there will be no more benefits from using a larger value of K once you get to a certain point. And we are seeing that here. And I bet, I don't know why I didn't do this, but I bet if you went up to K equal 20, you're not going to see a benefit either for going higher, a higher value of K. Now also, if let's say that you're really concerned about the correct classification rates for the failures and the successes, well then, this plot also gives you that kind of information too, and you can make a judgment of, well, can I live with a classification rate all the way down here if my success classification rate is really high? And that's a tough judgment to make. It's often dependent upon the actual problem of interest. Let me make sure I am recording. Good. Here's a question for you. as k goes to n, so imagine that we were to extend out that x-axis all the way to n, what's going to happen to the correct classification rate here for the place-keeping data set? Exactly. It's going to approach the proportion of successes that you have in your data set. So it's going to actually approach about, with the original data set, about 0.89. So to some respect, you can see, to use a mathematical term here, convergence to the overall proportion that it actually exists in your data set for successes and failures. And this will happen with any data set, that you will converge to that. So still overall, these methods are not necessarily doing any better than if you were just to simply say, okay, I'm going to classify everything as a success. These methods are not, working any better than that. I think, with like a k equal 4, I think we're getting a correct classification rate here of about maybe 0.87 when we actually observe about 0.89 successes in the data set. So to some respect, that's disappointing that we can't do better than just using a very simplistic method. Let's talk about how we. Well, first, are there any questions about this plot or choosing k? I would typically treat validation, associate a little bit more validity to the validation data set. Usually, but we have kind of an unusual circumstance in this particular data that we have just so many successes and not that many failures. And especially since the validation data set's a lot smaller, I think this is not giving us as good of a picture as we would like. The validation is. Other questions?
I'm sorry, I struggled to understand the intuition of picking 4 to 7.
Okay.
K. I guess when I initially glanced at it and I saw the validation data set that the overall was 92 for that first K, and it had such relatively high accuracy for the failures. That would have been my first instinct.
And that just goes back to the discussion from yesterday, or on Monday, where I am hesitant to attach a confidence to the results from the validation data set, especially for the lower values of K. That's the reason why. And also, if you notice, too, if you want to, and typically you should do this, use both cross-validation and validation. And you can see with the cross-validation, that's giving you a different feeling about what the value of K is than what the validation is. So, if you only look at the validation here, you might miss out that, well, maybe that's not correct. Other questions?
So it's not necessary that smaller the K, the better the choice.
Excuse me?
If not necessary, that smaller the K, the better the choice.
Well, the overall thing that's most important is the correct classification rate. Okay? And let's say a method had a 90% correct classification rate at K equal 4 and K equal 10. Well, which would you choose? Well, typically K equal 4 because it's going to be, to some respects, simpler. So yes, the smaller the K, the better. But the number one thing of interest is the correct classification rate. Okay, so let's briefly talk about how I did this plot, because I did some things that were just slightly different from maybe what we've seen before. So I'm going to jump on over here to 10. So first of all, I'm going to open up a kind of a wide graphics window. And then I'm going to use par mf row equals C1, 2 there. What that does, it creates basically a grid of plots, 1 row, 2 columns. Okay. I think we talked about this before. Does this look familiar? MF row, that option argument? Okay. Make frame by row, that's what that stands for. Okay, so the first thing I'm going to do is now do a plot. Let me actually get a graphic sheet up. I am going to do a plot of, on the x-axis, K. On the y-axis, I'm going to put the correct classification rates for the failures. I'm going to control my y-axis limits to be between 0 and 1 because that's the range, the numerical range for classification rates. Put some nice little grid lines on my plot. And then this argument's new. Type equal O. The default with a plot function is type equal P, standing for plot points. What type equal O says, plot the points, yes, and also draw lines between the points. And this is helpful in this situation so you can see trends as a function of K. So if I execute this code, you can indeed see that we have the points and we also have lines connecting the points. And then to get then the rest of the lines on the plot, I use the points function where I say, again, K for the x-axis, for the y-axis, the correct classification rate for the successes. I don't know why I put the y-lim there. I don't actually need the y-lim. But I again continue with type equal O, and I change the color to blue. And there you can see now for the successes, the correct classification rate. And I continue then for the overall rate. I use the AB line function to put that horizontal line on the plot for the best results from discriminant analysis. And then I use the legend function to plot a legend. So that's how these plots are done. The main thing was the type equal O argument that you had not seen before. Okay, so let's move ahead. I'm going to jump to page 16. We'll come back to stuff on page 14 shortly. So let's look at, for K equal 4, let's look at more specifically what the results were, and also let's look at some graphs that help illustrate what nearest neighbor classification is actually doing. So what I decided to do here was use the cross-validation method with K equal 4. I set a seed, of course, to be able to reproduce my results. And here's the classification tables. We see also the classification rates. So 94.6% are correctly classified for the successes on page 17, and 86% correct classification rate overall. Then I do some plots, again, to help get a better idea of what's going on here with these classifications. And since we have a lot of, well, we don't have a lot of variables, we have like 8 variables, what I decided to do was simply do principal component score plots. So you can see both 2 dimensions and 3 dimensions in the notes. We'll just look at the 2 dimensions here. And we see the successes are in red, the failures are in black. These are the classifications. And if you remember with principal component number 1, essentially it gets more negative as the distance increases. So you would expect more failures as the distance increases. And we can see that in terms of how the classifications are going here too, in terms of where the black ones are versus the red ones. But what's interesting that I especially like to point out is that you see blacks that are somewhat throughout throughout these point clouds, if you want to call them that. Now, the reason why I want to point that out is I want to compare it to what we got from discriminant analysis, and the best method that best results that we got from discriminant analysis. So on the left here we see from discriminant analysis, this is actually linear discriminant analysis with equal covariance matrices. And on the right is then the results from nearest neighbor classification. These are the classifications from both. You can see some big differences how decisions are made, in terms of successes or failures, in terms of the classifications. If you remember when we talked about discriminant analysis, I showed you all like a little plot that basically showed you, actually I can show it to you real quick again here. It's page 38. So if you remember, I showed you this plot when we have three different populations and how discriminant analysis works. It essentially draws lines between populations to try to come up with a classification procedure. And you can somewhat see that then with these principal component score plots. You see from my writing from previously that red line that I put there, you can see the lines being formed. Now notice with nearest neighbor classification, you don't have those lines. So you can see how nearest neighbor can be more flexible than discriminant analysis through this kind of a plot here. Of course, did the flexibility really help us here? Maybe only a little bit. But you can imagine maybe other applications where that flexibility potentially could help you. Okay, so let's also take a look at then, now I'm going to back up in the notes. I do exactly the same plots now for the validation data set. And I would like to point out that notice how you see some black dots on the right now versus what we saw before on the left. I actually re-ran a principal component analysis with the validation data set, got the scores out, and it just so happens PC number 1 had longer place kicks having positive values for PC number 1. If I had to do it again, I would probably just simply get the principal component scores for the validation data set through using the previous principal component analysis with the mono-billing or the training data set. I would have done that, but it's somewhat debatable which way is the most correct, but I did it this particular way in the notes. And again, from looking at this plot, what you're doing is you can see how these black points are kind of mixed up with the red points in comparison to what we saw with discriminant analysis. Okay, takes us to page 18. So how can we do variable selection here? Well, as similar to discriminant analysis, there's simply not a good way to do it. I guess ideally the best way would be to look at all possible models that one could form and get the correct classification rates from, or I should say all possible models, all possible combinations of variables that one could form, get the correct classification rates from all of those, and then choose the set that gives you the best overall classification rate. Of course, in the place-kicking data set, that means that you're looking at 2 to the 8 different variable combinations, which would be, let's see here, (256) different implementations of nearest neighbor classification. Think of all the different values of k that you might want to look at too, and you can see it becomes quite a large problem fast. So that's why simply, variable selection is often not done, or usually not done with these methods. Okay, some final notes then for this section. Well, we only looked at an example for an actual data example with just 2 populations. This stuff works for 3 populations, 4 populations, as many populations as you want. Still you can get these probabilities out of of which population that this observation should be classified into. The only disadvantage of using KNN or KNN.CV with getting these probabilities out is that you only get one probability out for each observation, and this probability will be associated with the population that the observation was classified into. I mentioned that briefly before. Just to make sure you follow my point, is that let's say you do have 3 populations, and the probability that you classify into population 1 is 0.49. The probability for population 2 is, let's say, 0.49 as well. And, oops, let's do 0.48. And also then for population 3, suppose it's 0.03. The problem, though, with KNN and KNN.CV is that you will only see this particular value. the highest probability. You will not see that, oh, population 2 was very likely too. You just won't see that. So you will miss some information about uncertainty. But that's just the way that this function's implemented. The second bullet then is kind of interesting. If you were to perform a discriminant analysis, and eventually the goal with doing a discriminant analysis is that you want to be able to apply it whenever you get new data or a new situation, or let's say a new place kick. You want to be able to apply this discriminant analysis that you've already just done, apply it to this new data. So, you can imagine, let's say, Bo Pelini on the sidelines, he takes out his tablet and he's trying to decide, should I actually attempt a field goal or not? Well, he could plug in the distance, he could plug in the wind speed, he could plug in all that stuff into his tablet, and up will pop out success or failure predicted based upon this training data set, this original data set that we've already had. And he could use that then to make a judgment, should he attempt a field goal or not. Now with discriminant analysis though, the only things that you actually need from this training, this model building data set are the mean vectors and also the covariance matrices, right? If you remember the formulas, that's all we needed. With nearest neighbor methods though, you need the whole data set still, because you are still looking for the distances that, let's say, a new situation, a new observation that you have, maybe a new field goal that you're thinking about attempting, you still need to compare that to all the previous observations that you had in your original training data set. So you can't throw away that training data. Where with discriminant analysis, once you get the mean vectors, once you get the covariance matrices, you throw out the data. You don't need it. Just kind of an interesting note about that. Well, what happens if you have a very large data set? Well, as you can see here, you could be calculating lots and lots and lots of distances. And so because of that, there have been fast algorithms developed to facilitate this process. If you are interested, you can take a look at the FNN package for functions that implement these algorithms. This last note on page 19 corresponds to something that we briefly mentioned in class. And let me actually go back to the page 1 of the notes to help explain that. Let's say k is equal to 2 for this particular plot, if you remember this from last time. And we want to classify the red dot. Well, if k equal 2, we have these 2 points as the nearest neighbor, and we would essentially have a tie. Half the observations from population 1, half from population number 2. But you can see that, the observation that's from population number 1 is a lot closer to the red dot than the observation from population number 2. So because of that, you might think, well, maybe the red dot's more similar to population 1 than it is to population 2. So essentially what you can do is you can weight observations based upon their distances. These weights are often formed based upon probability distributions. So in this case, I give more weight to the observation from population number 1, and I would classify it into population number 1. If you want to know more about that, there are functions available for you to do that kind of k-nearest neighbor classification. Take a look at the core learn package and the core model function inside of it. And then lastly, there are other distance measures that you can use too. It doesn't have to be Euclidean distances. There's some references there too if you're interested. Okay, that concludes our nearest neighbor classification. Are there any questions? Let's briefly talk about the project. You now have enough background to complete the project. And remember, you're using the weak kernel data set with this particular project. And simply what I would like you to do is, in a very similar manner to what we did with the place kicking data set, apply k-nearest neighbor methods now to the weak data set. Okay? So, part A. Determine an appropriate value of k. Well, we talked about how to do that with the place kicking data set here today. Basically, do the same kind of stuff. Just, of course, remember to set a C number. Do this before the for loop so I can reproduce your results. Use that seed number. Why wouldn't you want to use a seed number inside the for loop? Let's take a look at the code again. Oh, where is it? There it is. So why wouldn't I want to put, let's say, a set.seed right inside this for loop? Set.seed 4511. Why wouldn't I want to do that? Exactly. You're applying the exact same seed for every single implementation of the k-nearest neighbor method. Potentially, this could introduce bias because you're always using exactly the same seed number. Potentially. So that's why you do it outside the for loop. You set it once. Let's close that out. So part B then, with the value of k chosen, and guess what? That you may choose a different value than another group chooses, which will make my grading more interesting, I guess. Do cross-validation. Tell me what the correct classification rates are. Set a seed so I can reproduce your results. Yes.
So I have a question about the seed. If a seed inside the loop, it's like I can fairly compare all the different k, so that because different k have the same starting point.
Well, you're essentially biasing yourself because you're always essentially starting from the same place, and you're missing perhaps some extra variability that would be induced in a real-life problem by always using the same seed. That's like, for example, if you ever do a Monte Carlo simulation study, you could, suppose you simulate, let's say 100 data sets inside a for loop. You don't set the same seed every single time within that for loop because you'll get the same simulated data. Okay. Then part C, do some plots very similar to what are discussed in part B, or number 2B there, so that we can see where the correct classifications are, where the incorrect classifications are. So that's number 3. Any questions? Okay. Let's move on then to a new set of notes. Logistic regression. So, for those of you who've taken Stat 875, you have seen logistic regression before, but just in a different context. In Stat 875, we were very, very concerned about interpreting the effect that a particular variable has on the response. We are not going to be concerned about that here. Rather, what we're going to be concerned about is using these logistic regression models in the case of 2 populations. Again, 2 populations only. We're going to be using these models to help classify, is the observation from population 1 or is it from population number 2? In the next section, we will talk about multinomial regression models, and we'll talk about how can we classify observations into a case where you have, let's say, 3 or more populations. But now we're just going to talk about 2 populations. For those of you who have not taken Stat 875, I first of all recommend that you do take it. It is a very good class. We spent a lot of time talking about logistic regression in that class, and logistic regression is very, very, very well. It's used in a lot of different places because in so many different places, in let's say real life settings, you have a response that is binary. It has 2 possible outcomes. And so we talk about in that class, we spent a lot of time discussing, well, how can you analyze a situation where you have 2 possible outcomes. If you're interested in Stat 875, it is taught next semester. It's taught at 11 a.m. on Mondays and Wednesdays. What else did I say about it? First of all, the book for that course. I've actually written the book, And it's not fully out there yet in terms of published, so I will give you a PDF of it for free. So I have saved you $100. So that's reason enough to take the course. Also with the course too, we will be using a blended, also known as a hybrid teaching method, where we will generally meet only once per week. And a lot of the usual lecture that you see in this class will be actually moved to online videos. Especially for some of you who may be coming from maybe city campus, now you only have to travel to East Campus, typically once per week rather than twice per week. Okay, so if you have any questions, more questions about Set 875, just feel free to ask after class. So, talking about logistic regression. Let's first of all just real briefly review normal linear regression that all of you should have had some experience with in a STAT 801 kind of course. Here's what your model looks like. We have a response variable we call y. That's on the left-hand side. And on the right-hand side, we have a linear combination of some parameters denoted by betas with our explanatory variables, independent variables, or you could also call them covariates, denoted by the x's. Our epsilon term is our error term. We say that's distributed normal 0 sigma squared. Notice I have a subscript r on stuff up here in this model. That just is helpful for us to denote that this is for, let's say, the rth observation of interest. Notice that then for all observations, we have exactly the same variance for that epsilon. Then also, well, what would you expect y to be on average? Well, that epsilon simply disappears from our model because it has a mean of 0. And you're left with this linear combination of the betas with the x's. Also, one could show that the variance of y itself is just sigma squared. And so thus you could actually say what we're doing here is our model says y is distributed normal with a mean of this linear combination of the betas and the x's. So the mean can change as a function of your x's, and we have a constant variance for every single observation. And while this is this first model that I showed you above is the way that regression analysis is usually taught, I think in actuality it's better just to simply think of it this way, where all you're doing is saying, okay, y has a normal distribution with a mean that changes as a function of your x's and a constant variance. With this model, we're very interested in these betas, typically, because that tells you the effect that x has on the response. So if beta is greater than 0, it says that x has a positive effect, meaning as x increases, y increases. If beta is less than 0, you have a negative effect. If beta is equal to 0 itself, it says that x has no effect on y. So that takes us then to what a logistic regression model is. You see some similarities. You also see some differences. First of all, please correct this little typo there. I think I had a y that should have been a pi instead. Now, y is going to have a binary response. So either, let's say, 0 or 1. And in fact, what we're going to do, we're going to say instead of y having a normal distribution, y has a Bernoulli distribution. All of you should have seen a Bernoulli distribution in the past. In fact, we actually had talked about it in the factor analysis section. And y sub r, so for the rth observation, is distributed Bernoulli. And if you remember, Bernoulli has one parameter, pi. It's a probability success. Probability y is equal to 1. And this pi has a subscript of r with it, meaning that pi can change for every observation. The expected value of y, again, is pi sub r. Variance of y sub r is then pi times 1 minus pi. Now, what we're going to do then with logistic regression is that we're going to set pi to be a function of our explanatory variables. Just like what we did with the normal linear regression model, essentially this mean, this pi, is going to be a function again of our explanatory variables. And this is what the function looks like for a logistic regression model. E raised to now the linear combination of the betas with the x's over 1 plus e raised to the linear combination of the betas and the x's. So it's very, very similar to what we saw before, but now we have this little weird transformation of this linear combination of the betas and the x's. And just for emphasis, I'm going to put y, expected value of y here as well. Well, let's talk about this weird transformation that we see here. First of all, notice that the numerator of what's on the right-hand side of the model is always going to be less than the denominator. The reason being, first of all, exp, the exponential function, always gives you a positive value. And notice in the denominator we have 1 plus the same thing that's in the numerator. So we always get a value between 0 and 1. The reason why that's important is because probabilities are always between 0 and 1. Okay? Now, there are actually other transformations that you could do in order to get something on the right-hand side that's always between 0 and 1. For example, maybe some of you have heard of probit regression or complementary log-log regression. You have other little transformations there too. But the transformation that we're using here is the most commonly used and results in what people call logistic regression. Without going into all the details, basically, this transformation also gives you a nice little interpretation of the effect that X has on the probability of success, which is not the subject of this class, but the subject of Set 875. Now, what one could also do is through some algebra is write on the right-hand side of the model only that linear combination of the betas and the x's, just like what we saw with the normal linear regression model. And when you go through the math, on the left-hand side of your model then, you get this little transformation of pi instead. Log of pi over 1 minus pi. So log of the probability of success, probability y is equal to 1, divided by 1 minus the probability of success, or the probability y is equal to 0. So you can see that we're taking now a transformation of pi. If you look at it in this opposite way, you could say, this little transformation of pi is often written like this, logit of pi. It's just the name, it's just notation. People often write this more simply as logit of pi. And since it's kind of a pain to always attach this R subscript to everything, what you will often see people do, and I will do this too, is just you can rewrite the model without the R subscript, just so that you understand that this pi will change as a function of every observation. And so these are two equivalent ways to write the model. So suppose that beta 1 is equal to 0. What does that say about the relationship between x1 and y? Do we still have a positive relationship, as we did with the normal linear regression model? Yes, we do. So what that means is as x increases, the probability of success increases as well. If beta 1 was less than 0, that says as x goes down, the probability of success. If beta 1 is less than 0, that says as x increases, then the probability of success goes down. And let's just end with some nice plots then of this model. Let me actually blow this up a little bit. So let's just look at a particular situation where, let's say, beta 0 is equal to 1, beta 1 is equal to 0.5, and we only have one x, call it x1. Then if you look at the left-hand side here, you see a plot of that particular model. So notice as x is increasing, you see the red line increase as well. The y-axis is probability of success, or probability y is equal to 1. Sorry, people usually say y equals 1 is a success, y equals 0 is a failure, so that's why I've been using that versus saying the y equal 1 population versus y equal 0 population. And you can see here, that this this curve here kind of looks a little bit like an S to some respect. And so people often will refer to this as an S curve. You also see, for example, if I were to draw a line across like this at pi equal 0.5, you see what's above it. It's kind of a mirror image of what's below it. Just a characteristic of this kind of a statistical model. We can also see if I let beta 1 be negative, look what happens. Now the curve is going down. So as x is increasing, the probability of success, or the probability you're in the y equal 1 population, goes down. So, that's what our model looks like. And again, the reason why we're looking at this model is because we're going to look at then how we can make a judgment. Should this observation be classified as a success, or y equal 1, or should be classified as a failure, y equal 0? How do you think you should make that judgment? So if pi is greater than 0.5, how about you classify that observation as a success, or y equal 1? If it's less than 0.5, classify it as a failure. That's simply how it works. Very simple. But there's something very nice about using a logistic regression model versus the other stuff that we've done that makes it even more flexible. And that is, why should you use, let's say, a cutoff probability of 0.5? Now, it kind of makes intuitive sense. You have a higher probability. If it's being one population than another, using a 0.5 cutoff. But that doesn't mean you can't use a different cutoff probability. Why not use 0.6 or 0.7? So if pi is greater than 0.7, classify it as population 1. If pi is less than 0.7, classify it as the y equals 0 population. You could do that. And this can be very, very helpful in situations, especially when you're very, very concerned about the correct classification rate for, let's say, the y equal 1s. And maybe that's your really most important thing versus the overall correct classification rate. And so by changing this cutoff probability, you can greatly then affect what the correct classification rates will be for the y equal 0s versus the y equal 1s. And we'll look at ways to do that. That's one of the main topics of this section. Okay. Are there any questions? Okay, let's do course evaluations.